So stable isotopes as an analytical tool for determination of food authenticity. I have to use mouse. Okay. Food authenticity. So there are three aspects of determination of food authenticity. We can look at it from different perspectives to depending on what we want to obtain what information. So the first is the origin of raw material, which is used in food production, which means which kind of plants, industrial plants, fruits, for example, wine, grapes for wine production, etc. Then we have geographical origin of food product. This is indication of geographical location from where the raw materials is taken for production of specific food product. And we have originality or brand name and location of production. So like detection of like fingerprinting of a specific original brand. For example, is it Jack Daniel's whiskey coming from Jack Daniel plant distillery in Kentucky, or somebody took empty bottle original and put some cheap colored distillate and put back on the market. So these are three different aspects when we are talking about stable isotope, where they can help us. So first thing is, what are isotopes? So as I said, each atom contains protons and neutrons. It's written here. So the number of protons defines the element. Is it hydrogen, carbon, oxygen? You all know this. And the sum of protons and neutrons gives the atomic mass. But when we are talking about isotopes, they can have 1 or 2 or 3 neutrons more in the atomic core. So basically they have the same atomic mass, but they have a bigger number of neutrons. So for example, carbon has 6 protons and 6 neutrons, and it's written like 12C. Then I will switch on my video, so you will see when I'm talking. When I'm making like this means that compressor starts. Okay, so what did you hear what I said until now?
Yes. Yes.
Okay, so stable isotopes of light elements such as hydrogen, carbon, oxygen, nitrogen, and sulfur can give us information about food authenticity. Also, unstable 14C can give us also one point when we are talking about authenticity. And it is especially used for detecting of illegal, for example, illegal addition of synthetic ethanol to alcoholic beverages. How is that? So first we have to know how 14C is developed and where it is developed. So 14C naturally occurs in the upper layer of Earth's atmosphere. And because of neutron bombarding of from the cosmos in the upper layers of atmosphere, these neutrons are attacking nitrogen atoms, and nitrogen is converted to 14C. So in that way, we get CO2, which is carbon dioxide, but actually this 14C comes from nitrogen atoms, which is bombarded by cosmic radiation. So he is unstable, and he decomposes by releasing an electron in the reverse reaction, and he comes back to nitrogen 14. But this reaction needs time. So that's why it is very slow, and that's why we say that his carbon 14 carbon has approximately 5,730 plus minus 30 years of how do you say,
time for
not time, but mid not the full time, but the period of decay, but this is the half time. Oh, it's written here. In a minute, it's a half time, 5,730 years. So here on the curve, you can see that it will need more than exponentially it goes down. So it will take more than 10,000 years to decay totally, so that he comes back to nitrogen. This is a good thing for some measurements, and that's why we can use it for detection of to detect what is the age of some items, for example, in archaeology, to do some analysis of oil, because oil is underground in those basins, which are billions years of old. We can use it for some geochemical analysis of Earth and etc. But when we are talking about food, actually about alcoholic spirits, synthetic ethanol, we know that it is produced in industry, and raw material, it comes from oil, right? You get ethylene, synthetic ethylene, and then ethylene is hydrated to ethanol, and that way you get synthetic ethanol in chemical production. So this ethanol, because it comes from the oil, this means that he will not have 14C, because oil is very old. It was produced a billion years ago, right? And all this 14C is already decayed totally, so you don't have it. But all living things on Earth, including us, like humans, all animals, all plants, are breathing and assimilating CO2 from the air. So which means that 14C is also assimilated. We are taking in us. So we have it in our organisms. All trees, everything which is alive has 14C inside, integrated in our systems. So when something dies, this assimilation stops, and from that moment we can this 14C starts to decay, and after 10,000 years or more, it is totally decayed. So in that way, we can, for example, take ethanol from refined ethanol, whatever, from the plants produced in by metabolism of microorganisms, and this ethanol will have this 14C. So by using this kind of apparatus, this is Quantulus, this is scintillation liquid counter, we can differ between two different types of ethanol. Synthetic, as you can see in this picture here on the monitor, synthetic will have the basic line, which means that there is no 14C inside. But this green peak spectrum actually will give us the concentration of 14C in a sample which is from the plants, right? So by measuring these peaks, we can make different mixtures of synthetic and natural ethanol, which holds inside 14C, and we can make a calibration curve. So by taking different ratios of natural and synthetic ethanol, we can make actually calibration curve. And this means that this peak will grow bigger and bigger until it is 100% natural. So we can make mixtures plastically. 10% of natural ethanol plus 90% of synthetic, then 20, 80, 30, 70, and etc. to up to 100% natural. So this means that this peak will slightly go up, and then when we calculate the surfaces of these peaks, we can get analytical values, and we can make calibration curve for this. And according to this calibration curve, as any other analytical method, we can, in our sample, detect the amount of synthetic ethanol in specific alcoholic beverage, which is tested. So also this concentration, I forgot to tell this concentration of 14C in atmosphere is always in some kind of equilibrium. So you have pillows of this CO2 in upper atmosphere, and they are equilibrated. They are all in some kind of dynamic equilibration. And this concentration from year to year, it differs, but it differs for very small, actually very, very small differences. So approximately concentration of 14C in atmosphere is something about 14 dpm per gram of carbon. dpm, which means decay per minute per gram of carbon. So this is the unit which we are using for quantifying the 14C in analytical measurements. So after the Second World War, there were some nuclear testings, right, in Pacific Polynesia or some or Nevada, or in Russian Federation, in Russia, Siberia, wherever, but all around the world. So because of these testings of atomic bombs and nuclear weaponry, this concentration of 14C in the atmosphere was totally disturbed. So in that period, after the Second World War, this concentration of carbon was very, very high. And when these testing stopped, they stopped to do it. Then this 14C concentration exponentially start to lower it down, and today is again on the natural level as it should be, 14C. But it took 40, 50 years to come back to the normal level. So this line can be used for the concentration of 14C in the atmosphere, can be used for analyzing and saying if something is coming from the specific year. So is it 1968 or is it 1954 or something like that? So there are these data banks. They measured 14C in the atmosphere for years, and for each year they can say now from which year it comes. So this is another approach where you can say that something is coming from early history. But if you go further into past, before the Second World War, you will end in the the same natural range as we have it today. So before the Second World War, when we didn't have nuclear weaponry and everything else, we can see from those samples how old are they by decay of the carbon, concentration of the 14C carbon in them. So it is used. It is used for example, for archaeology, where you can say how, for example, this mummy or this sarcophagus is old. Is it 9,000 years? Is it 10,000 years? This all about this 14C. There are some problems with detecting, because different matrices, different kind of samples, they have different spectra. They don't have all spectra like ethanol here. They can be pushed, moved, different shapes and everything. So that's why technicians and actually scientists who are using this equipment, they need to make some quenching curves so that they can push the peak to be on the reference the same frequencies, so that they can compare the peaks and that they can quantify it. So this is very, very hard. It needs a very good knowledge in this area, and not so much laboratories in the world can do this. But to come back, how this instrument is working. So scintillation technique is based on a cocktail which is added to the sample, and he makes like he gives energy, right, to excite the solvent molecules in scintillation cocktail, so that he bombards this cocktail, bombarding a sample with particles, with electrons, I think. It was a long time ago, 15 years ago, when I started and I was working on this Quantulus. And it excites that the sample starts to transfer light. So this light is then accepted by specific detectors, and it is by software calculating the amount of this bombarding of these photons, actually, and it gives then it counts this and it gives these peaks. So yeah, that's it. But now, what we are more interested when I was starting with isotopes, the first thing I was working with this scintillation instrument. But since I'm a food technologist and my topic was adulteration of food and detection of food authenticity, I found out that stable isotopes can give us more information than 14C. So that's why I transferred myself to stable isotopes. So stable isotopes of light elements. We are interested in 5 elements. This is hydrogen, carbon, oxygen, nitrogen, and sulfur. So as I said, hydrogen, deuterium, and tertium, for example, they will differ in neutrons. So in that case, deuterium will have 100% bigger mass than hydrogen, because hydrogen has 1 proton and 1 electron, but deuterium has 1 proton, 1 neutron, and 1 electron. So his mass is 100 times bigger than hydrogen. The same thing is with carbon, but he will have 12 protons, the single carbon, but his stable isotopes will have 13 neutrons while carbon will have 12. And 14C will have, as I explained, 14 neutrons and 12 carbons. So their mass will be bigger for 1 or 2 neutrons. Oxygen also. In nature, they are found as 16O, 17O, 18O. Nitrogen 13O, but this is synthetic. Actually, it's 14N and 15N. And we have sulfur 32S, 33S, and 34S. So when we are talking about isotopes, we need their abundance in the, I will come back to this slide, but I have to come here so that you can see relative abundance. So in the nature, 99.9855% of hydrogen is hydrogen, and only 0.0145% is deuterium. For carbon, this is 98.892 versus approximately 1% is 13C. For nitrogen is 0.3663 is his stable isotope 15N. For oxygen, you will see that this 18O is 0.2, 17O 0.03, and 99%, 99.7586 is 16O. So how we measure them, because this is very small amount, how to quantify them. So if you take ratio between, for example, carbon, you take 12C and 13C. So you measure them on RMS, for example. I will explain the technique on the next slides. But you measure in the ionic beam, you measure how much you have 12C, and then on the other detector, you measure how much you have 13C. So you make this ratio between 13C and 12C. And this value will be like, you will get like 0.0000056 zeros, and you will have 1, 2, 3, for example, for one sample. For the other sample, you will have, again, 0.000, and then you have 1, 2, 5. So this is not, you cannot quantify it like this. So that's why somebody was thinking about it, and they made this reference line, like a reference level. And somebody said, okay, let's take a reference material, and we will measure relative ratio between carbon 13 and carbon 12 in this reference material. And we will say that this relative ratio for this is 0. And then when we are measuring our samples, relative ratio of 13C for per 12C, we will introduce delta values. This is this sigma here, sigma values. This represents deviation of the ratio of stable isotope in test samples, how much he differs in promille, on promille scale, from the reference sample. So in this case, you get real numbers in promille. It's not like it will be 0.0000. Now you will have 1 promille, 2 promille, 100 promille, 200 promille, etc. So this is the way how we quantify stable isotopes, by using these delta values. And we have different reference materials for different isotopes and for different matrices, which we are using. From that point, everything else is very much similar to all other analytical methods. If you want to quantify something, some analyte, you have to make a calibration curve, right? Linearity curve with different concentrations and of analyte you are analyzing. And then by putting your value that you are getting in your instrument for tested sample, you quantify by using linearity formula, and you get from your standards used, you get your concentration of your analyte in your sample. Very similar from this point on. Everything is very similar to all other. The concept is the same. So the principle of isotope measurements. We cannot measure everything. Actually, we can, because RMS is a technique which you can put garbage, for example, prepare a sample of garbage, and you inject into a peripheral for continuous flow, and you will get elemental gases, and you will get a relative ratio of, for example, 13C, 12C, this sample of garbage. And but what does it say? This is so the preparation of sample and isolation of the analyte which will be analyzed is very, very important here. And the purity of the analyte is even more important, because when we are talking about stable isotopes, it is very important that we don't have isotopic fractionation. One more thing. Now, I'm talking about everything and anything, and I will jump out of the presentation and come back. So, I said isotopic fractionation. What does it mean? So for general chemist, how do you say analytic? Analyst, general chemist analyst. For example, water is H2O. For isotopic analyst, it is not H2O. It is a variation of different isotopes which can and which are occurring in this water. So it can be H2O, it can be HDO, so hydrogen deuterium oxygen. It can be hydrogen H2 16O, H2 17O, H2 18O. It can be D2O. So there are different fractions of water, isotopically speaking. So when we want to, for example, to extract the water from some sample, we cannot do it by just simple distillation, because during this process we'll have isotopic fractionation. Some of these fractions of heavier molecules, which have heavier isotopes or lighter isotopes, we will lose them. So we need to think differently when we are preparing this sample. How to do this, but not to lose some fraction, so that we have complete picture, and that when we are analyzing the sample, that we get repeatable and reproducible results. So, for example, here, now I'm coming back here to this principle of isotope measurements. For principle of isotope measurements and determination of origin and statistic, for example, in wine, are based on a various interaction of plants and the environment depending on their morphology and physiology. So isotope ratios are specific for a certain type of plants and are directly related to the climatic conditions and area of plant origin. This specificity is also reflected in the final product originating from certain area, which represents an isotopic fingerprint. What does this mean? This means that, for example, if you have your grape or your fruits or your beet sugar produced in Turkey, it will have similar but not the same fingerprint, isotopic fingerprint, like we will have it here in Vojvodina. in Serbia because the climate is different. Local climate affects stable isotopes. So water, which comes from rainfall, it has a different isotopic profile. And all living, as I said, all living things and all plants, they are assimilating water, assimilating carbon dioxide. So they will integrate this into their plants, into their metabolism. So we'll have similar, but not quite the same fingerprint. So if we want to measure sugar from beet sugar from Turkey, it will have very similar carbon, but deuterium, for example, or oxygen in this will differ because of the water which plant uptakes. So by measuring the relative isotopic ratios of hydrogen, oxygen, and carbon in various product fractions, specific information can be acquired about the origin of raw material utilized in the production of wine or production of fruit products, or fruit juices, or sugar crystals, or sugar syrups, honey, etc. So according to CO2, so now we are talking about stable isotopes, right? We are not talking about 14C anymore. We are talking about 13C. So we have 13C also in the atmosphere. It is integrated in CO2 gas from the atmosphere. So according to type of metabolism, is it Hatch-Slack, is it Kelvin cycle, or intermediate cycle? I don't know if you know this from biology, if you had it on faculty or before faculty. But according to the way how plants are assimilating CO2, they have different metabolisms. So when we are differentiating plants by carbon metabolism, as I said, Hatch-Slack metabolism, Kelvin's metabolism, or this intermediate metabolism, we can say that in planet Earth, we have three types of plants. We have C4 plants, we have C3 plants, and intermediate metabolism, which is CAM plants. This CAM is Cassulaceae family of plants, which have this intermediate between C3 and C4 metabolism. Why is this 3 or 4? Because in one mechanism, you get the primary metabolic, which holds 4 carbon. And in C3 metabolism, you have 3 carbon as a primary, we can go further. So who are the main representatives of C4 and C3 and CAM plants? So as you can see here in the slide, corn and sugarcane are the main representatives of C4 plants. They are coming from tropical locations. So, and also not just them. You have sorghum, for example, in Asia. You have palm tree, also a C4 plant. I don't know, is there some else? You know, these 3 or 4 are the main representatives. 95%, on the other hand, 95% of plants on the planet are C3 plants. This means all fruits, all trees, or grapes, rice, industrial plants which are important to us, sugar beet, all kinds of grains, barley, whatever, sunflower, olives, everything is 95%. 95% of are C3. So these intermediate plants, chem plants, are mostly agave. This is cactus. What we get from cactus, we get tequila, which we don't drink here in Serbia, but it is very very used in Mexico and Latin America. So how we differ them by delta 13C value. So for C4 plants, this range will be from -8 to -13 per mil, as you can see here, per mil versus VPDB. So for carbon, we are using reference material VPDB. And this per mil, it means that delta value, delta can be written by like D or like sigma. Okay, so it means that if you are running samples on carbon for C4 plants, all these will be in this range that they will differ from VPDB reference material for 8 to 13 per mil in minus. For chem plants, it will be from -10 to -23 per mil versus VPDB. And for C3 plants, it will be from -23 to -30 per mil versus VPDB. So these are not so big differences if you're taking into consideration that, but they are very stable. So what this VPDB's reference material, it does not exist anymore. Only electronic value is already calculated in the software of RMS systems, and it is calculated electronically. Why? Because this VPDB was actually a sample of meteorite which fall down on Earth, and they use this meteorite, and they say, okay, we will take this meteorite as a reference material. So he's long gone, they don't have it anymore, but they have the value, and they are integrated this value, and they say VPDB is the reference material, and we will calculate all values, all samples, wherever you run RMS analysis according to this, so that you can get reproducible results. So what is measured? So this is for wine, but actually it can be, this slide is for wine, but you can use it for other types of samples. So carbon will give us information, differentiation between C3 and C4 and chem plants, right? What is it on RMS? Oxygen, for example, in wine or fruit juices, or in liquid samples, water sample, will give us information for food, for wine and fruit juices, for example. Will give us information, is it genuine, or it was diluted with water. So water is not allowed to be, wine is not allowed to be diluted with water. And oxygen can give us information if water is added. This is standard procedure. And by measuring non-exchangeable hydrogen stabilizer, this hydrogen is the most like a reference method which will differentiate. On hydrogen, we can differentiate between C3 plants. So carbon gives us information between C4 and C3, but since 95% of plants are C3, we need to find a way how to make a differentiation between sugarcane, sugar beet, all kinds of industrial plants versus fruits and grapes, for example. So deuterium and hydrogen relative ratio can help us in this. So application of isotope ratio analysis in food authentication. So for example, products you can see here for fruit juices, watering is deuterium and oxygen by using RMS. Fruit juices sweetening is delta 13C and hydrogen, deuterium, NMR. Honey is addition, we are detecting adulteration, addition of invert and cane sugars, and this table is old. In that time, there was only 13C RMS. But I will show you in this presentation other methods and other application for honey adulteration, how it is detected. So aromas, flavors, vanillin, raspberry, cotton, blah, blah. Also delta 13C, delta 18O on RMS, and also NMR, 2H NMR. Alcoholic beverages, mislabeling, geographical and botanical origin, again, RMS, NMR, different kinds of stable isotopes, carbon, oxygen, hydrogen. Wines, watering, it is like in fruit juices, deuterium and delta 18O. And for wines, chaptalization, it is delta 13C and 2H NMR, but now we have EIM RMS, which we developed, and actually it will become very soon also OIV resolution and international standard. So to come back for oxygen and isotopic fractionation. So ocean water is our reference because it's huge amount of water and it is somehow equilibrated. So water cycle in nature is will give us information where something was produced, how it will give us this. So we have a natural evaporation of water in water cycle, and water becomes water vapor, and then water vapor condense and make clouds, and then clouds make rain, and rain drops back to the ground. But clouds are going from the equator to the up north to the north and south pole. So they are depleting there is a isotopic fractionation of water in these cycles. So how it works, you have first ocean evaporation by sun, heat, it goes up, make clouds, and then goes north. So when it starts to condense, first the heavier isotopes are condensed and they drop back to the surface. Clouds become, isotopically speaking, they become more light. They go further into continents. They again rain, make rain more. The next level of higher isotopes are rained down, so they become more light until it comes to the poles where they make snow, and like snow, they are very depleted in deuterium and heavy oxygen, so they are these values, delta 18O and delta D values, are very negative compared to equator, which are which we say it's zero. So when we are using, when we are measuring water samples, and actually when we are measuring oxygen and hydrogen in samples, the reference material is ocean water. So somebody, not somebody, but International Agency for Atomic Energy, they make these reference materials, and they pick from somewhere in the world, from some ocean, I don't know which one, but they took amount of water, and for these samples we are saying that delta 18O, it is called V small, which means Vienna, standard, main ocean water, V small. And delta 18O for this standard is 0. And also delta D value is set to 0. Then you have V slap and GISP water standard, which are waters from Greenland and Arctic water. So they are depleted in deuterium and oxygen. So by using these three standards, these both like reference and these two standards, you can make a water line. It is actually for calibration and scaling, and you use these values, these 3 points, to detect, to obtain, to calculate your values in your sample. We are saying it is a water line. So now we are coming to EIM RMS. Oh, sorry, RMS. Very similar, actually the same instruments we have. This is delta 5 plus XP. We have it here in our lab. What was this is how we measure delta 18O in water. There are different kinds of techniques, but I will come to this. I want to explain the principle of a stable isotope or measurement. So RMS can be used for continuous flow technique and for offline techniques. Mainly it is used for continuous flow. So RMS is a mass spectrometer, but he can be connected to mainly three or less, or you can make 4 different peripherals which are connected to him. So in this case, we mainly use elemental analyzer. Then we use equilibration device. There are different types from different producers, from thermal, from elemental, from zircon, from instrument does not have. So these 3 are like major players for continuous flow and RMS instruments. So equilibration technique, and then we can connect HPLC, liquid chromatography unit, or GC, gas chromatography, coupled with some interface, and then connect it to the RMS. The point is that sample in continuous flow is converted to elemental gases like CO2, like nitrogen, like hydrogen, and CO, carbon monoxide. And we are measuring, dependent on the technique, we are measuring 13C, 18O, deuterium, or delta 18O pyrolysis of carbon monoxide. And yes, I said gas bench equilibration technique. So the main thing is that we produce first elemental gases, then we split them, because if you combust something in elemental analyzer, if you do combustion technique, you will get in presence of oxygen, you will combust the sample, you will get CO2 and water. You have to take water out, and CO2 then, when it comes to the RMS, first thing, he is bombarded by electrons in the filament, and in iron source, he is ionized. Then he goes through a series of lenses, electrical lenses, which are approximately here in iron source, and then he is like concentrated, like in one string, and like this, everything is in helium flow. Helium is used as a carrier gas, and then it comes to a very strong magnetic field, which is adjusted to specific intensity, so that in this field, this ionized gas of CO2, for example, is splitted into fractions. So after that, we have cups. These are detectors. Actually, these are Faraday cups. And these beams are entering into these Faraday cups, and they are detected as such. And software is counting the number of atoms, right? So in that way, you get these masses, 46, 45, 44. So in this picture, we have, it is presented like triple cup. This is 3 cups which are in the middle. But if you want to measure hydrogen stable isotopes, there are also 2 more cups which are, if you watching the proofs of the pointer, one is here and one is here. So one will measure hydrogen, the other will measure deuterium. So in that way, we will get mass 2, or mass 3 and mass 2. And by relative ratio, software calculates and gives you this relative ratio of specific fraction. And then it calculates delta D value directly from the software, from the option you choose. Faraday cage, it is like this. So coming to this is, for example, equilibration technique. This is gas bench. For example, if we want to, this is a technique which is used for oxygen in waters or wine or strong spirits, whatever. It is based on a principle that if you put in a vial, you put a small amount of your sample, and then in headspace you inject a mixture of helium and CO2. Helium is to preserve this atmosphere as inert gas, and CO2 is equilibration gas. Somebody thought about this, that oxygen from CO2 in time of equilibration will equilibrate with oxygen from water in the sample. So in next 8 to 12 hours on room temperature, there will be equilibration and exchange of this oxygen between carbon dioxide and hydrogen and water. And you will get at the end 16 in water, and oxygen 18 will go to CO2. And then after this equilibration time, you take CO2 from the headspace and through the gas bench peripheral, it comes to RMS, and by using this technique, you are measuring mass 46, 45, and 44 in your gas which you are analyzing, and then after that you get delta 18O in your sample. So and you are calculating it via V small, where V small is also prepared in the same manner like you are preparing this. So it means you put standard reference material, you put in vial, you also put headspace, you put the same gas, and you do the same procedure as for your sample, and you measure the carbon dioxide from V small, and then you are measuring your sample, and you will see the difference, and then you say, okay, I know that this is 0, so how much is then delta 18O in my sample? So natural factors influencing isotopic fractionation. Now we are going a little bit deeper into the topic. 20 minutes. 20 minutes. I have 20 minutes more. Okay. I will see if I can get in. So one of the biggest minds and scientists in this area was Professor Gérard Martin from University of Nantes. And he was trying to solve the problem to the detection of chaptalization in wine. And actually he gave he suggested the principle how deuterium is redistributed during glucolysis process, and where deuterium ends when sugar is converted via alcoholic fermentation to ethanol. So he found out that sites on sites deuterium which is connected to glucose sites 1, 6, and 6', they will end on metal site, while water from plant water will have the very big influence on methylene site, and that hydroxyl groups hydrogen from second, third, fourth, and fifth carbon will finish in wine water. Why is this? Because 80% of hydrogen deuterium atoms from hydroxyl groups of grape sugar are in constant dynamic equilibrium with surrounding water. This is exchangeable hydrogen, and he makes hydrogen bonds with surrounding water, and this is always changing. So after fermentation, they will come to wine water. So why is this important? Because Gérard Martin found out that ethanol is a perfect analyte which can give us information about botanical origin of plant. Sugar as sugar is not so nice, not so good. But ethanol, after alcoholic fermentation, gives the best results and clustering differentiation between different kinds of plants. So also for this hydrogen, which is hydrogen on hydroxyl group and water plant, how it influenced the methylene site. We can see it in this mechanism. We have 3 steps in alcoholic fermentation, but the third one has the biggest influence. Why? Because glycolysis goes up to pyruvate. From this stage, it goes different ways. Alcoholic fermentation is only one of these different kinds of metabolism. But in ethanol, when we are making ethanol, pyruvate is first decarboxylized. It takes out carbon dioxide, and it makes acetaldehyde. And then we have this NAD, non-disclosure agreement, NDA, NAD, nicotinamide dinucleotide, which is coenzyme, oxido reduction coenzyme, and he takes the protons from the matrix, which is surrounding water, and he integrates them to this carbon and oxygen. So this double covalent bond is converted to a single one, and you have hydroxyl group, and you have hydrogen on this first C atom. So in that case, you get ethanol. So if you add water, it means that your matrix will exchange. You will have a different profile, and NAD will take a different kind of deuterium or ratio of deuterium and hydrogen and integrate them into this carbon, and then we can see this. So this is just what I explained. So based on this knowledge, these findings, today son of Professor Gérard Martin is a billionaire. They patented this, and based on this NMR concept, today we have a system of national reference laboratories in Europe, all around Europe, where they are trying to detect chaptalization of wine and alcoholic beverages, and actually they are doing lots of things, not just wine and strong spirits, but also oils, I don't know, different kinds of sugars, everything, food authenticity. But this was the first thing they did. So it is under a roof of Joint Research Center. And first, this BevOps, which is Office for Wine and Strong Spirits, it was in Italy, in a very small town in North Italy called Ispra. But today it is moved to Gel in Belgium, and it's not called BevOps anymore. It is like a European Center for Controlling Wine Sector. And but what was the problem with all of this with Gérard Martin? I will come here. So Gérard Martin found that the deuterium ratio between deuterium and hydrogen on a methyl site of ethanol, this is this prim here, will differ according to the origin. So that C3 plants, C4 plants, for example, excuse me, we know that they are differentiated by carbon. So it will be from -8 to -13, right? So this is cane, sugar, corn, sorghum, etc. But as we said, 95% of plants are C3 plants. They have the similar fingerprint on carbon. So we need to find a way how to differentiate them. And this Gérard Martin, he was successful by sniff NMR. He found that deuterium on methyl site will give us this information. So we have these two clusters, which means that grape, for example, fruit juice, all fruits will go into this red cluster, while industrial plants like potato, sugar beet, all kinds of grains, they will go into this green cluster. But this scale here, this is the problem. This scale is in ppms. This is part per million. So differences are very, very small. So because of analytical parameters, for each method you have to calculate measurement uncertainty, and which means that your analysis has some uncertainty. You have to calculate it and to show it. This means that on these borders of this cluster, red cluster, you have some measurement uncertainty. What if your sample drops here in this on the border? Is it okay or is it not okay? So you have this precision limit. So this precision limit is not like it is 100, but it is 98.5. The border for red cluster. Also on this other side, you also have, it's not 96, but it is 97.5. So this free area here is not like 3 or 4 ppm, it is actually 1 ppm. And the problem is, now you have all of this, but this range here for grape is very wide. It is from 98.5 to 106.5. So what does it mean? For wine production, it means that if you add sugar, and in wine production, we don't add like 50% of sugar of different origin. Chaptalization is done just to correct alcoholic strength in wine for 1% volume or 2% volume. So it means that if you add small amount of sugar from beet sugar, different origin, and for example, your natural ratio of deuterium is like 104 or 105. This ethanol, with addition of beet sugar before alcoholic fermentation, he will start traveling to the left. But because of small amount, he will still be in this cluster. So clever French guys, they made up terroir. So, okay, how can we calculate this into money? Oh, let's think about terroir. So now this concept is used on European level for authenticating and detecting of geographical origin of wines with designated origin, which means like, is it from Tuscany? Is it from La Rioja? Is it from, I don't know, Bordeaux, for example, or some fort? Is it from Serbia, or whatever? So they are making huge, now every national reference laboratory in Europe is making huge wine data banks where they are taking original grapes from the vineyards. They are making laboratory wine, and they are analyzing it. They are taking isotopic fingerprint and they are putting into this wine data bank. So if tomorrow this wine, which is produced from that vineyard, from that specific producer, is suspicious, or they are suspect that it is adulterated or fabricated, or it's not that wine, they take this wine from the market, they do analysis, and they compare it to the twin from the data bank. So it's like for people, all of us, we have our fingerprint, and in this way they are fingerprinting wine production, and they are protecting designated origin of this product. Now everything of this is not just they are not taking just deuterium from the ethanol, they are taking carbon, they are taking oxygen from wine water. So they have a list of 4 or 5 different isotopes from the same matrix, and they say this is the fingerprint. And it is very tough for counterfeiters to make this fingerprint looks the same as original. First of all, they don't have original information from the data bank because these are top secret national bases. They are not given to third parties, and it is very difficult. This is submolecular level. You cannot do it these things very easily as a technologist. So you can make that you need 12% volume of strength, alcoholic strength in your wine, but you cannot make it that this isotopic profile looks the same as original, and they can check this. So, but still, this whole concept is worth billions. They are making these wine data banks for now 35 years. But still, we have big problems with counterfeit and a lot of illegal practices. And as I'm looking at very often to these reports from European Commission, these frauds in food are not just in wine, but also in cheese, milk, meat, whatever you want. There are huge police actions each month in European Union and worldwide. And you can see this on monthly summary of articles on food fraud and adulteration. This is, for example, January 2001. These are very often, these are very new. You can see 2020. So these frauds are estimated to be in hundreds of euros. And very often they detect by police actions, they detect these criminals, but after a few years, they cannot jump. And they are all over the world, European, there are huge networks of these fraudsters, and they are killing original and legal production, not just wine and strong spirits, but as I say, cheese, honey, fish products, meat, whatever. So that's why our company started to work on this problem, because we didn't see that NMR is helping so much. And we started to work on a new method which can give better information than NMR. So we did all kinds of different validations, comparison study to NMR technique and all other isotopic technique. For example, now this is a graphical preview of our EIM RMS method, which is now in official procedure, and soon it will be a new OIV method. So I'm the only one in 30 years that found a way to get information as Gerard Martin on his SNF NMR. So we are hoping that this will give better possibility for customs, for inspections, for national reference laboratory and all other laboratories to detect counterfeit products in wine industry, strong spirit industry, fruit juices, and from now we have honey. Yeah, we developed applications. We'll come to this. I don't know if I have more time. No. If you let me, yeah? You will not let me. So as you can see, we did comparison study. I will jump very fast here. We made, for example, with Russians, this study. That's the place where my wife Margarita and I met for the first time. We did this together, and from 21 adulterated samples, we detected 11 samples as adulterated, which means it is out of natural range which we get for grape ethanol. While NMR, which is this is CSQ NMR, but NMR is NMR. It is the same as SNF NMR from Gerard Martin. It detected only 3 out of 21. So and actually our analysis is just 2 or 3 minutes, and the SNF NMR lasts for hours per sample. So only 3 to 5 samples, or 5 to 10 samples, I don't know. But very small number of samples can be analyzed on NMR, while we can run 50 samples per night. So actually also our method can detect water addition because of that methylene site, and we detect also with our method. And this is actually the most we cannot say it is diluted water, but maybe it is another wine from this sky full of stars. Like that. So, but on the other, in other way, with EIM, we can detect additional water from ethanol, and it is detected as a legal practice. Honey is very important. Honey market is like, we in Serbia, we have almost 10,000 members of this national association, and we export our honey to Austria, Germany, Italy, and now it's bigger. It was 5,000 tons in recent years, but now it's more. It's 7,000 to 10,000 tons per year. So the same table I already showed you before about C3. Counterfeiting of honey. It can be direct, it can be indirect. Direct is when you're mixing directly sugar syrup with honey. Indirect, if you feed your bees with sugar syrup,